In this video, we would like to proceed to the next example. In the probability distribution to the right, the random variable x represents the number of hits a baseball player obtained in a game over the course of a season. Complete parts A through F below. Question A. Verify that this is a discrete probability distribution. In other words, we're going to first check each of the probabilities, and we observe that 1, each probability is a number between 0 and 1. Then 2, we're going to check the sum of all the probabilities. 0.16, let me put that on the bottom here, 0.1676 plus 0.3358 as far as 0.0233, which is the last entry here. We're going to check if that is equal to 1. You can punch that on your calculator and you'll find out that this is definitely equal to 1. Question B. Draw a graph of the probability distribution and choose the correct graph below. We're going to take these values, take them to StatCrunch, and deploy technology in graphing the probability distribution. Now, let's see what's happening in StatCrunch. I have the data set, and I'll go to Start, go to Calculators, go to Custom, select the variable in X, weights in probability of X, and compute. And here I have the graph of the probability distribution. So it goes up and then down. So this appears to be right skewed. So let's see, going back here, I can see that that seems to matches option B. This goes up and then there's a slide down. So my correct answer, my correct graph is this one. And to describe the shape of the distribution, we note that there was a going up and then there's a longer tail to the right. Based on our observations, we can see that this histogram has a single peak, which means it is unimodal. So we can say that the distribution has one mode and is skewed right, since its tail is pulled out to the right. The description we just read is posted here on the screen. The distribution is unimodal, that is, it has one mode and is skewed right. Then next, we would like to compute and interpret the mean of the standard of the random variable and the standard deviation of the random variable. The good news is when we're using StatCrunch, that is already computed for us automatically. So you have the mean here, 1.6246, and the standard deviation. So let's take that back to our working board. Here on the screen, you can see the mean and the standard deviation lifted from the computation earlier for the graph of the discrete probability distribution. So with that said, we proceed to the next question. What is the probability that in a randomly selected game, the player got exactly 2 hits? Looking back at the table, we can see that for x equals 2, the corresponding probability is 0.2859. So we write that as probability the number of hits x is equal to 2 is 0.2859 from the table. Remember, again, that comes from the table. And then, finally, we have to find the probability that in a randomly selected game, the player got more than 1 hit. More than 1 hit would be either 2 hits, 3 hits, 4 hits, or 5 hits. The corresponding probabilities would be summed up together, and that would be the answer for this case. So in this case, this is probability P. The number of hits, X, is more than 1, greater than 1. So that will be adding up all of these values: 0.2859, 0.1491, 0.0383, and 0.0233. Right here on the screen, I've written out all the probabilities, and the addition should be 0.4966 approximately. This is the probability that the player got more than one hit. If you choose to use the calculator, we can go back to Start Crunch, and right here, you observe that there are some observations here. This is the direction of the probability. If I click on this, I have some options, and I want greater than 1. And you will see that automatically it sums it up for you. So that's done. You have a calculator that can even help you through. So it means the sum of all the probabilities, or the sum of all the corresponding heights of these probabilities, is equal to 0.4966. StatCrunch is extremely useful and very helpful. You get the visualization to help with brain understanding, and you also get the correct answer. So that is done. And then we proceed to the next example. In this example, we are told that the graph of the discrete probability distribution below, or to the right below, represents the number of live births by a mother 50 to 55 years old who had a live birth in 2015. Complete parts A through D below. So we have the number of live births. It could go from 0 to 8. That is the random variable of interest. And the corresponding probabilities for each of the possible values of x has been provided with the dots here. So with that said, question A: what is the probability that a randomly selected 50 to 55-year-old mother who had a live birth in 2015 has had a fourth live birth in that year? In order to answer that question correctly, we simply need to focus on when the number of live births is currently at 4. We're interested in the probability. In this case, this will be probability that x is equal to 4, and that is equal to 0.113. Done. Then, the next question says, what is the probability that a randomly selected 50 to 50-year-old mother who had a live birth in 2015 has had a fourth or fifth live birth in that year? That would cover either this or this. So that will be probability of x equals 4 or probability of x equals 5. Well, if it is either this or that, that will be the combination of both of them. So we add up those probabilities: 0.113 plus 0.094. That will be equal to 0.207. Then for the next question, C: what is the probability that a randomly selected 50 to 50-year-old mother who had a live birth in 2015 has had a sixth or more live birth in that year? So that will be probability of x. It could be equal to 6 or more. That will be also greater than. So in that case, we need to, let me erase this, and we're looking at from equal to 6 right here, 7 or 8. So that will be 0.025, 0.035, and 0.057. This will be equal to 0.117. And then question D: if a 50 to 55-year-old mother who had a live birth in 2015 is randomly selected, how many live births would you expect the mother to have had? Well, the key word here is the expect word. So this is asking for the expected value of x, the number of live births. This is the same as the mean. So in this case, we will need to key in each value with its corresponding probabilities. in StatCrunch, and hopefully it can help us to do the computation fast. So let's head on over to StatCrunch. So here we are in Minitab. I have the different X values and the corresponding probabilities. Something to note in particular, for the number 0, we do not have any value given. So this tells us that the probability is 0. So I have keyed that in as 0 corresponding to 0. With that said, we go to Start, Calculator. We want our custom calculator again. Set our values to X and set weights to the probabilities. And hit the compute button. So we have the mean and we have the standard deviation. In this case, let's say we round this to one decimal place. This will be 3.1. So we have the mean. So with that said, let's go back here. So we have the mean of 3.1 if I round this off to one decimal place. Okay, with that said, we complete that question. And the next step is to review some inequality symbols. The reason why we are doing this review is we're going to need them in the next couple of examples and problems in the future. So for example, you want to recall that if I say x is at least, for example, x is at least 5, it means in mathematics that x can be equal to 5 or greater than 5. What about x is no less than 5? No less than 5 means the least value is 5. The only other direction it can be is greater than, because it is not less than 5. And x is greater than or equal to 5, that goes without saying. X is equal to 5 or greater than 5. Then you can have a slightly different variant. X is more than 7. That means x is greater than 7. And then if we have x is fewer than -3, it means x is less than -3, or x is less than -3. That goes without saying. That is it. Then what about if x is no more than 8? No more than 8 means x can be equal to 8. No more than 8 means it is bounded above by 8 as the highest value. It can only be what? Lesser. This is the same as saying x is at most 8, x is less than or equal to 8. All of these expressions are equivalent. Then what about if we have x is exactly 4? That would be x equal to 4, x equals to 4, or x is 4. All of this can be written this way. Soon, you'll see why this is relevant. It has been observed when teaching probability that the use of some words can be a little bit confusing. So, it has proven to be worthwhile over the years of teaching to first review these inequality symbols and their corresponding equivalents in English. All right, now we proceed to put what we just learned to use. In this illustration, let's say that you're working on a real number line and for the values of a discrete random variable x. Remember, at the beginning, when we learned about discrete random variables, they can only have values that are integer or whole number values, 0, 1, 2, 3, and so on. Now, the question before us is, you are only allowed to take a rest or stops at integer or count values, of course, since we are dealing with discrete random variable. In particular, what integer or counting values of x are captured by the range specified by this inequality? I'll keep it sweet and short and simple and straight to the point. Here it is. I see the number 2, I see the number 8, and I see less than, less than. Whenever I see this less than, it simply means all numbers in between. And if I'm thinking about discrete values only, then I'm only thinking about the numbers 3, 4, 5, 6, and 7. Numbers, discrete or whole numbers in between 2 and 8 to begin with. That is what this less than means. But then I have something extra, the equal to and the equal to. The equal to and the equal to here says, yes, I want you to include 2 and also include 8. So this range of values will be 2, 4, 3, 4, 5, 6, 7, and 8. That is the range of values covered by this expression. Based on what we just learned, what do you think about this? I still see less than. So first, I'm going to write every number in between 2 and 8, whole numbers in between 2 and 8 for discrete random variables. I keep emphasizing that in this case, we're talking about a discrete random variable because when we get to continuous, it might be something slightly different. So we continue. Do we include 2? I need to check if this is equal. Well, there is an equal to sign here. So that means I can include 2, but there is no equal to here. This is strictly less than 8, which means I don't need to include 8. What about the next one? Between 2 and 8, of course, 3, 4, 5, 6, 7. This time, do I include 2? No. So this means this starts exactly at 3. And then do you include 8? Yes. And then in this case, we're looking at strictly in between 2 and 8. So that'll be 3, 4, 5, 6, and 7. And next one says x is at most 3. At most 3 means it can be equal to 3. That is the most it can be. It can only be lesser. So this would mean you can go from 3, 2, 1, 0. That's it in this case. And the next one says x is at least 3. At least 3 means it can be equal to 3 as at the very bottom list, but it can also be greater. So it becomes from equal to 3, 4, 5, 6, 7, and so on. What about x is more than 4? That will be x greater than 4. And that starts from 5, 6, 7, and so on. Then we have x is less than 6 and greater than 7. So we want a value that is less than 6. Let's take 5, for example. 5 is less than 6. But this number must also, because of the keyword and, it must also be greater than 7. I find that difficult to believe. 5 is less than 6, but at the same time, it is not greater than 7. In fact, we cannot find a number less than 6 that is also greater than 7. So this is an empty set, written this way or this way. Then, lastly, x is more than 7 or less than 3. The key word here is the word or. It means I can choose, it only needs to satisfy one of the conditions. Either it is more than 7, like 8, 9, 10, and so on, or it is less than 3. That will be 2, 1, and 0 in this case. So those are the possible values or integer values that we're talking about here. Now that we have considered this basic review and an introduction to discrete probability distributions, we are now ready to learn about the binomial probability distribution. The binomial probability distribution is a special standard case of a discrete random variable. We shall see how that plays out in the next video.